is because over here I use natural logarithms, log with the base of e in my calculations, and they use log with the base of 10. And second of all is that mine use ideal conditions, ignoring the kind of attractive forces that arise along with the repulsion. So yeah, that teeny tiny bit of a difference is from that point. Anywho, this is very similar to Giegel-Sutter law, and it shows exponential decay as we always see in an alpha decay. So, what are the conclusions? There are three very basic, very interesting conclusions that I drew out from it. First one, radioactive alpha decay is only possible because of quantum tunneling. Second one, such process can never happen classically. Third one, whenever classical physics stops working, go quantum. And this is it. Thank you very much for listening to me. And if you have any questions, feel free to ask if you're not afraid of that person.
Who is this? Okay, good. That was nice. So yes, questions?
No, it was nice.
Okay. You? Come बच्चे? No question? Amount of quantum per day? Oh.
What about you, ma'am?
Okay, fine. Let's go
But
back.
it doesn't apply on you, though.
No, but why did you choose this?
It's a joke. Well, I wanted
Okay.
I wanted everyone
That's
to laugh at the
fine.
end of the
Okay, go
presentation.
back.
Yes, ma'am. Over here.
No, go further back. Okay. Okay, so can you give us some applications of alpha decay?
Oh yes, there are some very beautiful applications of alpha decay. I didn't choose to write it in my slides because there were already 10 slides, way too much.
That's fine.
But applications, we wouldn't be alive if it were not for alpha decay.
Okay.
If it were not for alpha decay, the suns wouldn't shine. The sun or stars in the galaxy wouldn't shine. Everything would have been cold. There would have been almost no nuclear fusion.
Okay, yes, that's quantum tunneling.
Yeah, quantum tunneling
Yeah.
and specifically alpha decay in quantum tunneling. And alpha decay is usually thought to be emission of alpha particles. However, if you go into details, it's just one of the types of alpha decay. And there are some more finer grades of it where helium-3 is released. Sometimes a deuterium is released. Sometimes a tritium is released.
The different isotopes of.
Yeah. So the reason was Coulombic repulsion gets the better of your strong nuclear force, and poof, it moves out of the nuclei.
Right. So what's the strong nuclear force?
Strong nuclear force is one of the four fundamental forces of nature that holds the atomic nuclei together. It is extremely strong. In fact, there was this number that while I was looking at a research paper that said that it is perhaps 10 to the power 5 times stronger than your electromagnetic force. Like ridiculously strong, but it is extremely short range. They exchange, you see, according to quantum field theory, every physical interaction that happens between two kind of particles, it happens by an exchange of a whole number spin particle. The whole number spin particle that is being exchanged in your strong nuclear force, it can be W and Z boson, and sometimes your pi and mesons. The W and Z bosons are actually used while the strong nuclear force is acting between the quarks of your proton or neutron. However, when two baryons or let's say, in fact, there are usually baryons present within your nuclei. So yeah, when two baryons, by baryons I mean neutron and proton, interact with each other, then they release a pi meson with one another that contains one up quark and one anti-up quark, perhaps.
Down quark?
No, there was this one quark and one anti-quark. I'm not sure if there were one down anti-quark and one down quark. I will look into my notes for this.
Okay, so next slide, please.
Yes, ma'am.
Okay, so we talked about the strong nuclear force, we talked about the repulsion. Okay, you go down. Okay, go down further. Okay, now you're talking about the barrier, right? So
I tried to give a classical intuition of what is happening in the quantum world.
Yeah. So can you give us some other example of barriers that we may have?
Oh, barriers, well, it's not always a hill and a ball.
Yes.
Yeah, it's as I said that we can talk about the gravitational potential of our Earth.
Yes.
If I want to leave this Earth, I need to have energy of this particular amount, that the velocity with which I leave Earth should be greater than my escape velocity.
Mm-hmm.
Alright? But it can, well, and classically speaking, it can never happen if my velocity is less than the escape velocity of Earth's gravitational potential energy, or Earth's gravitational potential. I would never escape the planet, classically. But quantum realm mixes the rules up a bit. That's why we call it the non-intuitive side of physics.
Do you think non-intuitive would be the right word?
Yes, it would be, because if, let's say I am standing over here, you're only seeing one muscle. I am extremely localized at one point, showing particle behavior, or at least a system of particles. You cannot see me over here or over here. As I said in the presentation, according to quantum mechanics, there is an infinitesimal chance that I might be on the moon.
So it's a probability, right?
Yeah.
Okay, so when I say example of a barrier, you talk about the gravitational potential, right?
Yeah, and that regular hill kind of a barrier.
Yeah, okay.
And yeah, there is another application of quantum tunneling too, and that includes the transistors of the laptop that you're using.
Electronics, yes. So
Yeah.
we talk about a potential barrier there
Yes.
as well, yes, of course. And then you can apply it to other things like solar cells.
Yes,
and
exactly.
So these are many, it's not just an abstract field, it has very practical applications, right?
Yes.
Okay, great. And opposite to the potential barrier, what's the opposite concept of potential barrier?
An opposite concept of a potential barrier?
Of,
Quantum tunneling.
you know, we have a potential
Yes, ma'am.
barrier,
Yes.
and the opposite would be?
So a place having no potential? Ma'am, let me draw a diagram to get the idea of what you're asking. Actually.
Okay. So normally when we do this in
I'm drawing a regular infinite scale well. Should I?
Yeah, that's what I was talking about.
Okay.
Yeah, right.
Infinite scale well.
Okay, and the opposite is the rectangle.
Yeah,
Yeah.
it's a rectangle.
Yeah, you showed it with a hill, but
Yeah.
normally when we do the derivations, we show it with a rectangle.
I use the rectangle
Yeah,
too.
yeah, yeah.
I use the rectangle too. Yeah.
Yeah.
You see, this is the rectangle.
Yeah, yeah. So a barrier would be a repulsion, right?
Yes.
And a well would be
Something that attracts
an
something
attraction,
towards you.
right? Good. Okay. So you've given us the concept of probability versus position, right?
Yeah.
And what's the little wave up there?
Well, it was actually defining that this wavefront is what defines the particle wave. It's just for the reference of it. It doesn't tell us about the particle. It's a key.
Okay, right. And if you come down,
Yes, ma'am.
okay. So this is a very good diagram. In fact,
I drew it myself.
seriously?
Yes.
How?
By using MS Paint.
Wow, it's really good.
Thank you.
It's very good. But for I can see it better on my laptop. But for presentation purposes, you should.
Yes, that's why I was asking him to increase the resolution of that.
No, it's not a matter of resolution. You could increase the size of this diagram. You know, I can do it right now if you give me a second.
Yes, ma'am.
So, but it will not affect what you because we're using different laptops.
Yes, ma'am.
So, one thing you should keep in mind whenever you're making a presentation, right? From the presentation point of view, is that maximize the size of the diagrams, and also you take a reasonable font size. Because,
Yes,
for
ma'am.
example, okay.
Actually, I thought that we would be using those like big kind of projectors that are